Neutrinos without secrets. End of the Borexino experiment. Work on the Borexino experiment, which has lasted over 2 decades, is coming to an end. This international project proved that energy is created in the Sun in various ways. The changes that occur in neutrinos on their way to Earth have also been observed. Neutrinos from the Earth's interior were also studied. Work on the Borexino project began in 1996. The detector itself collected data in the years 2007 to 2021. Now the experiment participants finish analyzing the data and summarize their activities. What did this extraordinary experiment reveal to us? Explains Professor mwyKQ, head of the group of physicists from the Jagiellonian University participating in this project. We cannot look into the core of the Sun using conventional astronomical methods. We only see the surface of the star in all ranges of electromagnetic radiation. Only neutrinos allow us to directly observe the solar boiler where energy is generated. And yet it is thanks to this energy, among others, there is life on Earth, explains Professor mwyKQ. Therefore, for 14 years, scientists have been observing neutrinos coming to us from the Sun and analyzing their properties to better understand what is happening inside our star. We owe the Sun's energy to the nuclear fusion that takes place there. As a result of this fusion, the nuclei of the lightest element, hydrogen, combine to form the nucleus of a heavier element, helium, releasing particles carrying a lot of energy. Such nuclear fusion on the Sun can occur in 2 ways. The most important is the so-called PP, proton-proton, cycle, in which 99% of solar energy is produced. A series of nuclear reactions, initiated by the fusion of 2 protons into deuterium, led to the formation of a stable helium nucleus. The second way to achieve nuclear fusion, 1% of the Sun's energy, is the so-called CNO cycle, where the formation of helium is possible in the presence of other elements, carbon, nitrogen and oxygen, which play the role of a catalyst. Borexino allowed us to thoroughly understand not only how the PP cycle works, but also for the first time observed the existence of the CNO cycle. This cycle plays an important role in energy production, especially in larger stars. Another important achievement of Borexino was the study of the so-called neutrino oscillation phenomenon, i.e., the transformation of neutrinos from one type, flavor, to another, in the low energy area, from several hundred keV to a dozen or so MeV. Neutrinos have the property that, when moving at speeds close to the speed of light, they can change their state, e.g., from an electron neutrino to a muon neutrino and then back to electron neutrino. These are the so-called neutrino oscillations. This transformation depends on whether neutrinos move in empty space or in dense matter, such as the interior of the Sun, explains Professor mwyKQ. As part of the experiment, the so-called geoneutrinos, antineutrinos from the interior of the Earth, they come from the decay of radioactive isotopes, in the 238U, 232Th chains and from the beta decay of 40K. Based on the geoneutrino flux measured in the Borexino experiment, it is possible to determine the amount of heat generated in the radioactive decay of uranium and thorium inside the Earth. Analyzers showed that this is a power of 38 terawatts. 1 terawatt is 1,000 billion watts. This value agrees well with the amount of heat escaping from the Earth's surface estimated by other methods. The geoneutrino measurement confirms that the main generator of heat emanating from the Earth is radioactive decay, concludes Professor mwyKQ. A physicist from the Jagiellonian University explains that neutrinos are probably the most common elementary particles in the universe. They are created during a number of processes, such as radioactive decay, nuclear fusion in the centers of stars, or as a result of supernova explosions. Every second, billions of solar neutrinos penetrate our body completely unnoticed and undisturbed. Very rarely, however, a neutrino interacts with matter. The chance to learn about neutrinos is to catch these unique collisions. This can be done using very sensitive detectors, carefully shielded from cosmic radiation and natural radioactivity. Therefore, the detector in the Borexino experiment was placed in the Italian underground laboratory in Gran Sasso, in one of the branches of the 10-kilometer highway tunnel running through the center of the Gran Sasso mountain range. The thick layer of rock that protects the detector weakens cosmic rays by more than 1 million times. In addition, the Borexino detector had an onion-shaped shape. Its subsequent layers, heading towards the center, increasingly better protected the interior of the device against natural radiation, originating, for example, from rocks. Nearly 300 tons of the so-called liquid scintillator. These are substances in which a flash of light appears when a high-energy particle hits them, e.g. a fast neutrino from the Sun. These flashes were captured by super-sensitive light sensors. There were over 2,000 photomultipliers installed in the detector, which, like the sharpest eyes in the world, looked into the interior of the detector and searched there for even the subtlest flashes of light. So the experiment, from a layman's point of view, was quite strange. In the middle of a mountain, in the Egyptian darkness, they looked for flashes of light from the Sun for 14 years. But this crazy idea worked. Professor mwyKQ reports that the number of solar neutrinos penetrating the Borexino detector in one day was in the order of 1,000 billion, 10 to the power of 21. However, the number of recorded interactions of neutrinos with the detector in one day was around 200, which allowed them to be examined well. The Borexino detector achieved an unrivaled level of purity in terms of radioactive contamination, which gave it a unique and unrivaled position among many low-background experiments. A group of physicists from the Jagiellonian University made a dominant contribution to achieving the unprecedentedly low background of the Borexino detector. This special feature was a necessary condition for collecting invaluable data during over 10 years of conducting the experiment, comments Professor mwyKQ. To sum up, the legacy of the Borexino experiment is not only discoveries in the field of astrophysics and neutrino physics, but also pioneering technologies. Innovative technologies were related to the unprecedented purification of liquids from radioisotopes, especially the liquid scintillator, and the acquisition and purification of appropriate materials for the construction of the detector using original methods. The Krakow group made a dominant contribution in this field, summarizes the researcher from the Jagiellonian University. The experiment was conducted in cooperation between physicists from Italy, Germany, France, Poland, the United States and Russia. The Borexino detector is already dismantled. This was necessary due to social protests in nearby towns, because the scintillator filling the device was a toxic aromatic hydrocarbon. Therefore, residents feared that this compound would enter drinking water. However, many other experiments are underway in the underground Italian laboratory. For example, the Dark Side project is looking for dark matter particles, and the Gerda Legend program is aimed at discovering the occurrence of extremely rare double neutrinoless beta decay. Parasitic black holes can eat stars from the inside. Sun-like stars may have absorbed tiny black holes that formed at the dawn of time when they formed, new research suggests. These black holes present inside stars can slowly consume material from their host. This, in turn, could produce an effect that could be detected. New research led by astrophysicist Earl Bellinger of the Max Planck Institute for Astrophysics and Yale University analyzed the possibility of star parasitism. The work suggests that Sun-like stars could have absorbed tiny black holes that formed at the beginning of time. These objects would gradually absorb material inside their stars, creating more tiny black holes. This is quite an intriguing concept. In the study, scientists analyzed the impact that such parasitism would have on stars. Scientists have also determined how we could recognize such stars if we came across them. The results and description of the research were published in the Astrophysical Journal. Black holes in the universe exist in many sizes. We know of masses of stars that were most likely formed as a result of the merger of huge, dying stars and the collapse of their cores. Every galaxy contains supermassive monsters ranging from millions to billions of solar masses. There are also rare black holes with intermediate masses. Hypothetically, miniature black holes could also exist. Scientists have suggested that such small objects could have been created in the first seconds after the Big Bang, when the matter of the universe was still hot and dense enough. This concept was proposed by Stephen Hawking in the 1970s and has since been expanded by other scientists. Primordial black holes, unlike ordinary black holes, would be relatively low mass, as black holes go. Scientists believe that these hypothetical objects could be created not as a result of the collapse of a massive star under the influence of its own gravity, but directly from the extremely dense material present in the first phase of the expansion of the universe. The varying densities of the early universe could have created pockets so dense that they would collapse into black holes. They would not be subject to the size constraints of black holes from collapsing stars and could be very small. Primordial black holes may provide an explanation for the excessive gravity in the universe, which is believed to be caused by dark matter. According to some experts, they could also be absorbed by stars and devour them from the inside, like some cosmic parasite. For their study, Bellinger and his colleagues estimated what would happen to a star formed around a primordial black hole with a mass ranging from 0.8 to 100 solar masses. They also performed evolutionary simulations of Sun-like stars with primordial black holes lurking inside them. Simulations showed that the smallest black holes would have difficulty expanding. It would take billions of years to eat the star from the inside. But the larger ones, with the mass of even a dwarf planet, would be more voracious. They would consume the core of their star, creating a spinning accretion disk around them that would begin to produce enormous amounts of light and heat. We found that such objects could be surprisingly long-lived, with the lightest black holes having no impact on stellar evolution, while more massive ones would consume the star over time, causing a number of noticeable consequences, the researchers write in their paper. Thermonuclear fusion would stop powering the star. Instead, this star would be powered by an accretion disk spinning around the black hole. All light would be produced by the black hole. Scientists have named this hypothetical type of star Hawking stars. Such a star would behave similarly to a normal star, with a few key differences. Its outer layers would swell to form a red giant, just as the Sun is expected to do when it burns up its fuel. However, with the parasite inside, it would have happened much sooner. However, the resulting red giant would have a lower temperature than we would expect from such a star. Interestingly, we have already found anomalously cool red giants in the Milky Way. Scientists say we could study these stars for black hole signatures. Black hole accretion would be expected to produce patterns inside the star other than mergers, which could be detected as small changes in brightness on the star's surface.